Hello. Today, let's see search in a rotated sorted array. So it's just that we are given an array and it's rotated from a random position. So in that array, we need to find a target element and we need to do it in log time. So if you can see here, the array, if we see the array in ascending order, it's 0, 1, 2, 3, 4, 5, 6, 7, but it's rotated from here. So the position 0, 1, 2 is kept after the array, and this makes it a rotated array. And we need to find the position of the target. If it's present, we return its index. If not, we return -1. So let's see how we can solve this problem. So let's consider this example. The elements are 4, 5, 6, 7, 8, 9, 1, 2, 3, 4. So we have the indexes here. So we need to find the target in logarithm time. So how do we go about solving it? So if we can split the problem into binary search, we can find the target in logarithm amount of time. But to make a binary search, it should be in either ascending or descending order. But as you can see, it's not in either of those. Okay. But if we look clearly, portion before the pivot 4, 5, 6, 7, 8, 9 and the portion after the pivot 1, 2, 3, 4. Both of these are in ascending order. Right? This is an ascending order and this is an ascending order. If the target is greater than or equal to 4, we know that target will be in this range. If not, we know that target will be in this range. So, to split the problem in this way, what we need to do is find the pivot. We need to find where the pivot is. So as you can see here, the pivot is at index 6. Okay. So how do we find the pivot? Again, we can use binary search to find the pivot as well. Now let's compare the binary search logic and see how we can implement binary search over here. Okay. So in binary search, the stopping condition is that if we are given an array and if mid is equals to target, then we stop. Okay. In binary search. Over here, how do we know when to stop? If we look at the pivot, okay, if we look at 1, it's less than its previous and next element. But no other element has this property. Only the pivot has this. So if you take this element, okay, it's greater than its previous, but it's less than its next. Or if you take 3, it's greater than its previous and it's less than its next. But only pivot is both less than its previous and its next element. So in our search, we will stop when and next element is also greater than mid. Then we know that pivot is at mid. Okay, this is the first condition. Now in binary search, we will move position of low and high boundaries so that we can narrow in on the target. So it's like this. So when position of mid is greater than target, high to mid -1. Okay, so how do we know how to adjust the boundary? Yeah, let's look at it. So we need to know whether we're on the left position of the pivot or right position of the pivot. How can we know that? If we are on the left position of the pivot, we can observe the property that any element in the left position of the pivot will be greater than or equal to the first element in the array. See, all the elements in the left position, 4, 5, 6, 7, 8, 9, all of these are greater than or equal to 4. So, if our element is greater than left, then we know that we are on the left position of the pivot. So what we do is we make low equals to mid plus 1, or else what we do is the third condition is else we make here the third condition is so I've just change the conditions. These two are similar. These two are similar. Okay. So this is similar to binary search, except that we add in specific conditions on when to change the boundaries and when we know that we have reached the pivot. Alright. Now let's see the code. So first I'm finding the pivot. Okay. So I'm doing a binary search, and when mid is less than mid minus 1, since it's the previous, mid plus 1, it's the next. If mid is less than both previous and next, then we know that we found the pivot. Okay. As you can see here, I'm doing plus 1% n and minus 1% n. So this is for the cases where when pivot is at the end of the array. So here the pivot element is at the last. Okay. So its next element is at index 0. Okay. So if I want to compare it with the next element, what I need to do is I cannot do mid plus 1 because it will be out of bounds. So what I do is mid plus 1% n. It will circle back and go to the element at 0th index. Got it? Similarly, mid minus 1% 1. So if this is the case, okay, this is the pivot. If you want to check the mid element 0 minus 1, that would be not a valid index. So what we do is we add the length of the array, and what do we get? %6. It's nothing but 5. So this is, it corresponds to the last element. So now we can find what pivot is. When we know that the mid is less than the first element of the array, then we know that we are on the right portion of the pivot. Then we put high equal to mid minus 1. If not, then we know that we are on the left portion of the pivot. So then we put low equal to mid plus 1. Now, by the end of this while loop, we would have found where pivot is. Alright. Now that we've found pivot, what we do is we check whether the target element is it in the left or in the right boundaries. I mean, if is it on the left side of the pivot or is it on the right side? Okay. So if it's on the right side, then we do a binary search on the right side, starting from pivot till the end. If not, we do starting from the 0th index till pivot minus 1. We do a binary search and we return the index. This is the standard binary search code. When we find target, we return it. If we know that mid is the element at mid is greater than target, we reduce the boundary of high. If not, we move low equal to mid plus 1. If it's not found, we return minus 1. Alright, yes, that's pretty much. Thanks for watching.